This next lesson bit is about the geometric distribution for discrete random variables. However, we're going to actually kind of go back and set this up with a fairly lengthy example, a little bit of reintroduction to probability notation and that sort of thing to give you a more formal background to a lot of this sort of thing. So it may take us a while to get there, but let's start with an example that will have a big payoff in terms of applying this later on. Okay, so let's actually look at an application of strong motion earthquakes. Right, and where we have measured somewhere the Richter magnitude and the number of events. And what we're going to do here is, with this log scale of the Richter magnitude, we're going to have recorded the data in terms of discretizing it, not continuously, but, or rather I should say, we're not going to look at it as a continuous random variable. Instead, we'll look at it as a discrete random variable that has values of 4 with a range of plus or minus 0.5, and likewise with 5, 6. So if we had an event that was 6.4, we'd lump it in here to 6. In this particular location, we've recorded over that sample time frame 87 events that were in that region of 4 plus or minus a half, 11 in that 5 plus or minus a half, and only 2 in that 6 plus or minus a half. Conveniently, that adds up to 100. And one reason why we start this lower bound at 4 is because, from an engineering standpoint, ground motions that are associated with Richter magnitudes less tend not to have anything significant happening to the building or the structure. And so our interest starts here, and even here we don't have usually a lot of structural damage. There might be some cosmetic damages associated with that. You also find out once you get into structural engineering associated with earthquake engineering that Richter magnitude is not a very reliable way to estimate what kinds of demands are placed on the structure and how much damage you might have. It's one of the very difficult aspects about predicting not only the occurrence of earthquakes, it's a whole other issue about seismology, but also predicting the effects of earthquakes begin to be quite difficult. Right? So before we go too far, we're going to introduce a new concept that we haven't talked about, and that's really the histogram. It's really a part of our descriptive statistics section, but you've seen histograms before, and it's a nice graphical way to visualize this data, and it's going to lead us into the continuous random variable world. And so I'm going to go ahead and introduce it here. And so we've characterized or discretized our data centered on these integers 4, 5, and 6. And if we plot here the number of events, then our first one is a real large bin that has, of course, 87, and then drops way down to 11, and then even further down here at 2. And we've got nothing on our record that says that we have earthquakes that are larger than that. And that's typically, when we look at data, our first thing that we're going to do. Now, another very common thing that we might do as we're looking at this data is to normalize it. That is, let's look at relative frequencies. That's real easy in this case, right? Because we've got 87 out of 100, 11 out of 100, 2 out of 100. So we're already thinking in terms of, I don't care how many, I care about what the percent of these are, which is going to lead me at some point to start thinking about what's the percent chance that I might get a magnitude of a certain kind of level. Right? And that's the big key, right? That what's the probability of future events. And one of the ways we use past history is to simply use it to predict what's going to happen in the future, right? That's the statistics using us to look into the future. So the simplest way we might do this is to set our probability of the future equal to the observed frequency. And if we did that at each and every observed frequency, if we did that for each and every possible outcome, then we'd have, in a sense, a perfectly tied model. It may not be applicable anywhere else, but it might be perfect for at least modeling the past. Right? So let's make sure you understand a little bit here about our probability notation that we're using. Notice this really doesn't have anything to do with the geometric distribution yet. I said this is a long build-up, and we'll get there eventually. When we talk about random variables, then oftentimes we'll use these capital letters, and some people like to be stylized and put the little serifs on there so it looks like a black Roman kind of letter. And here in our example, that was the magnitude of a randomly selected event. And for us, then the probability that x was equal to 4 in our discrete view of this was equal to 0.87, or 87% chance. Now in the continuous view of this would have been the probability that x was between 4.5 and 3.5. But in our discrete view, we just lumped all that at x equal to 4. And again, from that sort of discrete model view, only specific integer-like outcomes, then the way we talk about these observed frequencies from now a modeling standpoint, not from looking back in the past and statistics, is with the probability mass function. You've already seen this if you've done the reading in order that it was assigned, but if you've kind of hopscotched around, then you might not have seen that particular phrase or term yet. So probability mass function, and a lot of people will use then the symbol P for that probability mass function, put the subscript for the random variable, and then they'll italicize the argument of that, and that means the probability that our random variable is equal to that specific quantity. Sometimes they'll put the little subscript I to emphasize that it's not a continuous variable, there's only specific discrete outcomes. But the key thing being here that there's your random variable and there's your argument. And boy, that would have been nicer if I'd done that in a different color. So let's do that. That's our probability notation that we use over and over. Your textbook, or a lot of different textbooks will use just lowercase f here. I don't like to do that because I like to differentiate between the continuous random variable and the discrete, which is what we're doing and working with right here, especially for the geometric distribution. So I like to use just the lowercase p here. Right? Now, in terms of why we're doing any of this, you're either trying to understand what's happened in the past, or you're trying to look and predict about what something is going on in the future. And with earthquakes, it tends to be that. We're trying to make some sort of prediction about the future. So we get very interested in how to fit analytical models, because that's what we'll use to make those predictions. And one of our constraints when we do that fitting exercise is going to be that if we sum all of our probability masses over the possible outcomes, that total probability has to be 1. And here we're finally going to get back to what this little mini lesson is about, and that is in the geometric model, which is a probability mass function that looks like one constant times a second constant raised to the x power. And in this case, I've shifted it because I'm going to only include values of x equal to 4, 5, 6, and so on. Yeah, I understand that in our observed frequencies we didn't have 7, 8, or 9 or larger, and actually you can't get much larger than Richter magnitude 9. I think something around Richter magnitude of 10 or 11 the Earth splits apart or something like that. So this is just a straightforward shift here, sort of redefining where the origin is, x minus 4. But we really only have what looks like 2 parameters, but it'll turn out because of that constraint that we actually will ultimately end up with only 1 parameter to choose from. Okay, so how might we go about doing that? Let's go back to our data, our strong ground motion data, right? And so our x values that were possible were 4, 5, 6, and greater than 7. And our observed frequencies were 0.87, 0.11, 0.02, and we observed 0 that was larger than that. Okay, now it turns out if you go back to your Calculus 1 or Calculus 2 days, or you might have encountered it perhaps somewhere else, that if we go look at our series back here, our constraint that we have with this specific model, that when we sum all our xi, px of xi, with the geometric model, set it equal to 1, we're going to find out that b must equal 1 minus a. And that's why I said there's really only one parameter. And again, we've used that definition of our basic definition of probability functions, that summing over all the mutually exclusive outcomes, we have to have total probability of 1. Okay, so with that, alright, so that shortened things down here. Of course, the question becomes, well, what should A equal? If we could only find it, you know, bam, there you go. Okay, so, yeah, gee, what do we do? Well, what we could do is we could go back to the idea that we want the probability mass model to look exactly correct for as many of the different observations that we have. Right? So in this geometric model, if we fit at x equal to 4, then A is going to be equal to 0.87. Right? Just put the numbers in here. Right? If at x equal to 4, b to 4 minus 4, that would be b to the 0, so that becomes 1. So that means that at x equal to 4, our observed value has to be 0.87. Bam. That's how we got our A value. And when you propagate that on down, now we know what A is and we know what B is, because B is 1 minus A. Then we'll find out that we'll have 0.113 for the model view at x equal to 5, and we'll have 0.0147 at 6, and then we can find all the other ones here by doing 1 minus, right? Because if we've done these are our first 3, then the odds that we have something greater, yeah, I know the observed was 0, but the theoretical model is going to say there is actually a chance out there. So we'll do 1 minus 0.87, minus 0.113, minus 0.0147, etc. And you get a number that's pretty tiny, 0.0022 for our theoretical fit. Okay. Now, if instead we fit at x equal to 5, right, we still have the same shift of 4 up here, but if we fit here, we'll find out that our let's see, how would we do that? Oh, interesting question, right? If we fit there, probably, okay, so that means this is going to be raised to the 5 minus 4. So b times a, and, okay, b has to be equal to 1 minus a. All right, it becomes a quadratic equation, right? You'd end up with that at x equal to 5. Let's just write this out here, right? We'd have a times 1 minus a raised to the 1 power, and that has to be set equal to 0.11. That's our observed value there. Okay? And when you do all that, work out the numbers, you find out now that a is going to be 0.874, and we'll have a 0.11 there, a 0.0139, and 0.002. So now our model, if we were really interested in what happens at x equal to 5 in terms of earthquakes, would perfectly match what we observed in the past. Problem with that is that we don't really know if this is the right rate that we should observe at this particular one, right? This data was maybe only recorded over 100 years, but the Earth has been around a lot longer than that. Whether you like the creationist theory or you like the Big Bang theory, it doesn't really matter. The Earth is certainly longer than 100 years old, right? So our earthquake record, in terms of collecting data, is of a small sample. And wow, there's a lot of interesting questions then about how we take the information we do have and apply it to a broader scheme, broader model. There's even a more interesting question there too about how do you get that data and what happens over time. For instance, in the 30s, the United States Postal Service masters were required now to report earthquake data. So all of a sudden there was an explosion in the number of earthquakes in the United States. Well, not an increase in the number of earthquakes, but an increase in the number that were reported. And wow, that's a big difference. And of course, there's all kinds of interesting research about how you do archaeological digs to infer from that trenching, for instance, in looking at the soil strata, you can actually infer something about both the occurrence of earthquakes at a particular region and even to some extent what that magnitude might be. Right? But here again, the big picture here, and you could rerun this exercise for at x equal to 6. And if we do that, then we find out a is equal to 0.846, and our other numbers are, as you see here. Right? And we get some significant differences in an area that might be of real value to us. That is, the real demands for a structure are way out here in the tails. And so that raises the issue of that this model that we've developed, and it's true of the geometric model, is only tied to one actual observation or actual piece of data or information. And it does so without interest to the other data. And so now you've got to ask yourself, well, wait a minute, what's my real goal here? And, you know, in the end, what you really want is a model that minimizes error in the area of interest. Right? This is all about models. It's not about the real thing. It's about an artificial representation of the real thing. Right? And so, where is our interest in the sample space? In this specific case, it'd be out in the tails. We care more about strong ground motions that are very large, extreme rare events than we do about maybe the little baby earthquakes that might happen on a more relatively day-to-day kind of basis, geologically speaking. Right? So that's a real important part when you get into modeling. Now, in manufacturing, oftentimes you're actually more interested in the body of the distribution than, say, you are way out in the tails. And that means that we might approach things in a slightly different kind of effect. Or I'm sorry, we'll approach things in a slightly different way that will end up creating significantly different kinds of effects.